All right, there we go. So if you watched the video on Thursday, I started with this. All right, so the molecular formula H2O, and there's a Lewis structure below that. In that Lewis structure, I've drawn two covalent bonds between the H and the O. Okay, so everybody know what this is? What this represents? Anybody want to say it? Water. Hey! I thought that's beat. So this represents water. Now, had I not drawn that up there, if I just said the word water, what would you guys think of? Yeah, you'd think of rain or a river or an ocean, substance. So you showed that. There's some water. We live in the East. We get a lot of water. We can waste it. Right? Nice, clean water. You have to have it to survive. That is what water really is. And all of you know water. Okay, so this semester you'll be in lab. You're going to see clear liquids. Not all clear liquids are water. I hope we know this. Probably intellectually you know this. But I mean, you guys at this point in your lives know water like deeply instinctively. Okay, you know what water is. If you get water on you, you feel it. So in the lab today, you're going to use ethanol in water. Maybe not today. Not all of you today. But there's also acetone in there. At some point in the semester, you'll use things like hexane and ethyl acetate. These are all clear liquids. But they will feel different. Now, I'm not supposed to tell you this. You should wear gloves, safety glasses for sure. But at some point, you're going to get some acetone on you, some ethyl acetate on you, and it will feel different. Right? So these molecules have a reality. So water is real. This is how we represent a molecule of water. Right? That Lewis structure represents a molecule. It's obviously a lot bigger than an actual water molecule. And so what this structure is, you've got a hydrogen atom. It's covalently bonded to an oxygen. That oxygen is covalently bonded to another hydrogen atom. You probably remember, you said no red. Right? There's a polarity here. The oxygen is more electronegative than the hydrogen. So it's a covalent bond. The oxygen and the hydrogen are sharing 2 electrons. Right? So this bond, covalent bond, so that is, the covalent bond are 2 shared electrons in a bonding molecular orbital. I'm going to try to slowly filter some molecular orbitals in. We're not going to do a ton with it, but it's important to talk about it. Not sure that's all the way. Don't get dizzy when you watch this at home. All right. So, if you see a line like this, you should think electrons. Those are electrons. When we do bookkeeping for formal charge, which we'll get to here in a minute, we think about the electrons being shared equally. The electrons are not usually shared equally. So if one atom is more electronegative than another, right, that oxygen is more electronegative than hydrogen, that means it wants the electrons more, and so it winds up that most of the electron density in that bond is on the oxygen. That leaves the hydrogen with a partial positive charge. We show these partials with a little lowercase delta. Okay, so the other thing here is a neutral oxygen is going to have 2 bonds and 2 lone pairs. And you guys know this, all right? So you need to know this. You need to know this sort of just instinctively. You need to be able to calculate it, as I'll show you in a minute, but you also just need to know it. And what I'm telling you is you do, because you know H2O. Everybody in here shook their head, said they knew that H2O is water. Like seriously, if you watch The Simpsons starting when you were 2 or 3, you saw H2O every now and then. So H2O is something you know. That oxygen is neutral. Water is not a strong acid or a strong base. You know this because you can drink it, you can lay in it, you can wash your clothes in it. Right? If it was a really caustic substance, when it rained, you would dissolve. Okay, so water, you got water, let this anchor your knowledge. And so then you can also find the conjugate base of water. We'll do acid-base chemistry in the second set of the semester. So on exam 2 stuff will be acid-base. If you look at the schedule, we're going to do chapter 1, chapter 2 kind of today. Starting Thursday, I'll be doing chapter 4. We're going to skip 3. So exam 1 is going to be chapters 1, 2, 4, and 5. What have I just drawn on the board there on the left? Hydroxide ion. You said ion, so what's the charge? And where does it go? Yeah. So, look at that. Pull the red last. There's a negative formal charge on the oxygen. I'm going to indicate formal charge in this class by writing either a minus or a plus and circling it. So not +1 or -1. And here's the thing. This is organic chemistry. You guys all know this. Organic chemistry is the chemistry of carbon compounds. So compounds that have sort of a core of carbon. And you're all looking at me like, you haven't drawn a carbon yet, dude. Water plays an important role in biochemistry. So organic chemistry and biochemistry. If you do the etymology on these, they mean the same thing. The way they've divided out more recently, so organic chemistry, when it was founded, late 18th, early 19th century, it was the chemistry of carbon compounds, but also of living matter. Right? So most of the biomolecules that make us go are organic molecules. The bulk of our mass is water. Right? But if you get rid of the water and you get rid of the skeleton, which kind of keeps us upright, everything else is an organic molecule, and all the chemistry that's going on, like I said, that I can eat a bowl of Cheerios in the morning and then walk to class and wave my arms and draw stuff on the board, that's all organic chemistry. So the way we divide this, organic chemistry is the chemistry of carbon compounds in general. It doesn't have to be related directly to a living organism. All right? So if a living organism, dies and gets crushed for hundreds of millions of years, it turns into oil, and we pump it out of the ground and we burn it, that's organic chemistry. That would not be biochemistry. Biochemistry is much more specialized in that it is still the study of chemistry related to life, but directly related to life. Biochemistry is just organic chemistry happening in water in something that's alive. Okay, so this class, Orgo 1 and 2 lead pretty much directly into biochemistry. General chemistry is a little different. And so right now, I'm sort of, water is what kind of bridges those two divides, right? The inorganic chemistry, a lot of the chemistry you do in Gen Chem 111 involves water. Organic chemistry, like water is not an organic compound, and yet you have to have it for life. Okay, the other thing that happens then in organic, and this, if you think I've gone off the rails so far, I could go way further off the rails. We basically focus on the second row and above. So carbon, nitrogen, oxygen, the halides, and hydrogen. Like that's as much of the periodic table as you guys need to know for this class. You need to understand how the periodic table works, be able to read it. In terms of knowing and where you look, it's always going to be carbon, nitrogen, oxygen, halides, hydrogen. That's pretty much it. Sulfur will come in every now and then. Maybe a phosphorus if we're lucky. But most of organic chemistry and most of the chemistry that makes you guys go is that. Okay, so water's going to bridge this. The reason I can use just a minus or a plus is we're going to stay in the second row. Second row elements obey the octet rule. So an atom's not ever going to have more than 8 electrons. Sulfur might, phosphorus might. Again, third row and below, atoms can have more than 8. Second row and above, no more than 8. Hydrogen can only have 2. Right, so again, you know the bonding of hydrogen. Hydrogen is going to make one covalent bond. Water. Think about the structure of water. So this negative means that the oxygen has a formal negative charge. Now the charge on a molecule will always be the sum of the atomic formal charges. So here, the hydroxide, you called it the hydroxide ion, and that's technically true. The negative charge covers for the entire ion, the entire molecular ion. But if you think about electronegativity, the electrons are going to be preferentially on the more electronegative atom, and so this formal charge works out really well. We'll see an example here in a bit where it doesn't work out very well to describe the chemistry. The other thing is you should be able to calculate the formal charge. Like I said, I'm repeating stuff from Thursday's class because I want everybody to see it in person. You should be able to calculate a formal charge. And the equation for this is the number of valence electrons minus the number of lone pair electrons. So not the number of lone pairs, but the lone pair electrons. And then minus half of the shared electrons, or the bonding electrons. Right? So again, this is bookkeeping. And we're going to say that the two atoms equally share the bonding electrons. It's obviously not how the electrons get distributed. Okay, so but for bookkeeping, we're going to say that. So for up here, for the oxygen in hydroxide, this is going to be 6 minus 246 minus a half of 2. Right, so 6 minus 6 is 0, half of 2 is 1, so the oxygen has a negative 1 charge. The hydrogen, 1 valence electron minus half of 2, or 0. So the hydrogen is neutral. The hydrogen with 1 covalent bond is neutral. About that? It's hydronium. I haven't drawn one of the lone pairs. The next thing I'm going to do, like very often in organic chemistry, I'm not going to draw lone pairs in. You're going to just need to know that they're there. I also haven't drawn a formal charge. All right, so if you hadn't already seen hydronium, if I wasn't reasonably sure most of you had seen H3O, this would be a big problem. In point of fact, you cannot correctly draw a molecule without drawing all the formal charges. The only times in here that I will not draw the formal charges, the only reason I'm going to do that is so that I can quiz you or test you on it. Right? A correct molecular structure has to include the charges. So what is a charge?
+1.
Where is it? Where's the formal charge?
Is divided between the hydrogen.
That's good. So there's one lone pair. That oxygen is going to have 1 lone pair. So the oxygen is going to have 8 electrons. Oxygen, being an extremely electronegative element, really is always going to have a full octet. Right? It may be positively charged, but it will have 8 electrons. Okay, so formal charge on the oxygen is going to be 6 valence electrons minus 2 lone pair electrons, and then minus half of 6. Right, so there's 1 bond, 2 bonds, 3 bonds. Each bond is 2 electrons. That blue bit that I erased there said that a covalent bond is 2 shared electrons. So a bond is always 2 electrons. 6 minus 2 is 4, minus half of 6 is plus 1. So that oxygen has a formal positive charge. You knew that the hydrogen was neutral, so you said that H3O, the molecule, has a positive charge.
Yeah.
If you look at the hydrogens, formal charge-wise, those hydrogens are neutral. They have 1 bond. I'm very nervous now about the camera. Sorry. Yeah, that all looks on there. Okay. So, like I said over here, hydroxide, OH minus, 1 negative charge, and we put it on the oxygen. And sure enough, if you look at the chemistry of hydroxide, that oxygen behaves like it's negatively charged. Right? It's the more electronegative element. It's pulling all the electron density to it. So even in the OH here, right, this bond is polarized. So if you look at the dipole of an OH bond, the hydrogen's more positive, the oxygen's more negative. That is true in all 3 of these molecules. All right, so H3O plus, the oxygen has a positive formal charge, and yet the OH bond is polarized, so the oxygen is partial negative, the hydrogen's partial positive. So the statement that the positive is sort of on all 3 of the hydrogens is, in many respects, a true statement. Okay, so basically you can imagine kind of a third of a positive on each of those H's. So now let's look at this. I'll go ahead and put lone pairs in. I'm going to stop doing that at some point. So if I mix hydroxide and H3O plus hydronium, a chemical reaction takes place. I'll give you like 30 seconds. What's the chemical reaction that happens? Draw the products. I'm going to put my red pen away. I definitely want to use it. This is actually equilibrium. What are the 2 molecules that get produced? 2 waters. So we end up with two molecules of water. Those are neutral. So this equilibrium, not because it's neutral, okay? So we'll talk about equilibria when we get to acid-base chemistry for real, but this is an acid-base reaction. The equilibrium lies quite far to the right. Water is one of the more stable molecules in the world, universe. Hydroxide and hydronium are not. But if you think about this reaction, by formal charge, the oxygen is negative on hydroxide, it's positive in the hydronium. You would think that negative and the positive would make a bond. Maybe you wouldn't. If you wouldn't, just shut me out for a minute. Logically, if you'd never taken a chemistry class before, positive and negative attract. Why don't those two make a bond? And the reason is, if that happened, the way this would have to work, the hydroxide would need to make a bond to that positive. And the result of that would be that the oxygen that's positive would get more than 8 electrons. All right, so if we make an OO bond here, maybe don't draw this. not sure my green's going to show up very well. It looks pretty. Okay, so that oxygen all of a sudden has 10 electrons. Violates the octet rule, can't happen. The other thing, and again, this is going to be exam 2 stuff. I'm an organic chemist, so I really can't talk about chemistry without putting it in here. But this curved arrow, we would call that a mechanism for the reaction. And we're gonna see that a lot in this class, starting right after exam 1. That curved arrow means if the arrow always starts with electrons, and it would say this lone pair makes a bond to that atom. So that's not what happens. And the reason is, again, the polarity is off. Remember that even though the formal positive charge is on that oxygen, the polarity of the OH bond has the oxygen more electronegative than the hydrogen. So the hydrogen has a partial positive, and now the mechanism instead looks like this. All right? So one of the lone pairs on the hydroxide, that oxygen makes a bond to a hydrogen. All right? So these 2 electrons on the oxygen are making a bond to the hydrogen. Remember, a bond is 2 electrons. So a lone pair can turn into a bond. A bond can turn into a lone pair. Okay, so O makes a bond to H. That H can't have more than 2 electrons. So it gives up the 2 it's sharing with the oxygen. Those electrons go to the positive oxygen, neutralizing it. Negative atom gives away electrons, becomes neutral. Positive atom gains electrons, becomes neutral. All right, you're not going to have to draw mechanisms anytime soon. Don't freak out about that. My point in all this, you need to be able to calculate formal charge. You need to be able to identify the formal charge on a carbon, nitrogen, oxygen, or halide, just sort of at a glance. How many bonds does it have? All right, that would be, I don't want to say stupid. It would be very difficult to do for the entire periodic table, especially once you get down into the transition metals that have like 12 different oxidation states and can adopt all these different geometries. But in the second row, it's easy. All right, and then the other thing you need to be able to keep in mind, and this is hard, you need to be able to calculate formal charge, but formal charge does not always reflect how the chemistry is going to go. So there are quite a few molecules like hydronium where the formal charge is on an atom that doesn't chemically behave that way. Right? That oxygen is formally plus, but it's the hydrogens that behave like the positive atom. All right? We're going to see that a fair amount. Okay. I think I had 10 minutes budgeted for that. That's good. All right, so a little bit to work on here. I've just drawn a more complicated molecule, and now this is an organic molecule. Finally, we're to organic molecules. So a lot of you told me you watched the video from the other day, so I'm going to jump ahead. If you didn't, just hang in there. I have drawn an organic molecule the way I'm going to draw them all semester. I haven't put in any lone pairs. I haven't explicitly drawn most of the carbons. And I've only shown 2 of the hydrogens. but there's more there. So I'll give you like 60 seconds or so, come up with a molecular formula, and then we'll talk about how we got there. If you want to go on down, if you get the molecular formula and you want to do the next questions, that's great. You guys, I'll be back in a minute.